Okay, in this video, I want to tackle 4 difficult 3D geometry problems. There's a couple ways we could go about this. I already posted the notes for this video, so you can download the notes and then tackle the problem on your own first. And if you did it great, come back to this video and check your answers, or you could just watch the video and look at how I would solve the problem. There's actually multiple ways to do these problems, and you have all the tools already. But let's look at the problems, and feel free to pause and try to see if you can solve it on your own if you're so inclined. I promise you'll get more out of this video if you attempt it first. Okay, let's look at the first problem. So compute the distance between point and a plane. So we have some kind of plane. So I'm going to just kind of draw some kind of plane, and the equation of this is 5x plus y minus z equals to 1. And we have a point not on the plane, and we want to compute the distance from the point to the plane. So I just want to clarify the problem right off the bat. Plane consists of lots of, like, infinitely many points, right? And there's different distance to all of those points on the plane. But really, when it asks for the distance between point and a plane, what they really mean is what is the closest point in the plane to the point? Like, what's the shortest distance? That. Okay, so that's what we're going to compute. There's a couple ways to go about it, but probably the quickest way to do it is using the projection. So let me tell you what I mean by that. So first, we pick any point on a plane and call it, oh, I shouldn't call it P, because this point is called P. That's the point 1, 2, 3. So let's pick some point Q on a plane. And this one doesn't have to be the closest point. I'm just gonna pick a point Q. And how do I do that? Well, we have an equation that the plane satisfies. So we could plug in x and y, and then set what z is. Solve for what z is if we give it a given x and y. So I like simpler points. So I'm just going to plug in x equals to 0 and y equals to 0 into this equation. Okay. And if the point were to satisfy this equation, then negative z has to be equal to 1, or z is equal to negative 1. So what did I just do? I just found that the point 0, 0, negative 1 satisfies the equation of the plane. So it sits on the plane. Okay. Now what do I do next? I'm going to draw a vector from Q to P. And why am I doing this? Well, what I'm thinking is that, well, Q and P isn't the shortest distance between the plane, but if I cast a shadow in the direction of the normal to the plane, so remember the normal vector for the plane it points in the perpendicular direction, that tells you the shortest direction you can take to get to the P from the plane. So if I take the vector QP and project the shadow in the direction of the normal vector, I'll get this distance that I want. Okay, so I hope that made sense. I'm going to first find the vector from Q to P. So I'm going to take the coordinates of P and subtract the coordinates of Q from it. So 1, 2, and 3 minus -1 is going to be 4. And I know the normal vector for the plane are the coefficients of x, y, and z in the equation of the plane. So 5, 1, -1. And here, I want to cast a shadow of the vector QP onto the normal vector. So what I want to do is comp QP onto vector n. I just care about the distance, so I don't need the vector. I just need the component in that direction. So I take the vector, dot it with n, normal vector, and I divide by the magnitude of the normal vector. Okay, let's compute the magnitude. So 5 squared plus 1 squared plus -1 squared. So that's square root of 27. Okay. So 124 dotted with 5, 1, -1, all divided by square root of 27. So if I take the dot product, I'll get 5 plus 2 minus 4 over square root of 27. So 3 over root 27. And I guess I could simplify this further. I mean, square root of 27 is, well, 27 is 3 times 9, and 9 is 3 squared. So I could pull out 3 out of the square root and cancel it at the top. So I get the distance is 1 over root 3 here. Okay, all right. So that's this problem. And I should mention maybe one other way you could definitely do this problem is to find the closest point on the plane. So I'll just kind of give you a hint at how you might go about this. If you have a point in a direction, you can write down the parametric equation for the line passing through that point, going that direction. And n points in the closest path from P to the plane. So you could try to find the intersection of that equation, the parametric equation of the line with the plane. So you can kind of, once you get the x, y, z formula for the line, you can plug it into x, y, z here in the equation of the plane, and then solve for the t where it intersects. And once you get the point that's closest on the plane, you could use the distance formula between those 2 points to get the distance. So I'll leave that up to you if that method made more sense. Okay, let's look at the second problem. So I want to compute the distance between point and a line. Okay, so we have some line. It looks like we're given a parametric equation of the line and a point. You can see that I'm very not creative when I come up with coordinates for the point. Okay, so 1, 2, 3. And I want to know the distance between them. So again, if I'm finding a distance between point and a line, I'm really looking for the minimum distance. What's the closest point on the line to the point? Okay, so you could do this problem in a similar way as I did last time. So I know a point on the line, right? 150. Okay, I can call that point Q on the line. And what I could do is again draw a vector QP, and then I don't have a normal vector this time, but I do have a directional vector. For the line, which is -1, 1, 2. So that allows you to compute the vector projection in the direction of the line. And that what that does is you could get the vector that's pointing in the same direction of the line. What you care about is perpendicular direction. So what you could do is you could take the vector QP, and if you subtract away the parallel portion, then you get, this is QP minus the vector projection. And once you get that vector, you just have to find the length of that vector, compute the magnitude. Okay, so that's one way to approach the problem. I think I want to do something different this time. I'm going to use Calc 1. So what I'm going to do is I'm going to compute the distance between any old point on the line with the point P1, 2, 3. So the distance is going to be 1 minus t minus 1. So I'm looking at the coordinates on the line, and then I'm looking at the difference with the point 1, 2, 3. 5 plus t minus 2 squared plus 2t minus 3 squared. Okay. And then this is the distance at a particular point when t is equal to a certain number. I want this to be the smallest possible. And so I can try to, this is a function of one variable. So I can take the derivative, set it equal to 0, and then find the minimum of the function. But I can make the problem even easier. Instead of minimizing this distance, I can minimize the distance squared that will happen at the same point, but I don't have to deal with taking the derivative of square root, which is a little bit of a pain. Okay, so I'm going to call this function, instead of d squared, I'm just going to call it f. Take the derivatives that are equal to 0 and then find when the minimum happens. But before I do that, let me square everything out and maybe it'll be a little bit easier to compute. So let's see. 1 minus t minus 1. So that simplifies down to t squared. 5 plus t minus 2. So that's t plus 3 squared. Plus 2t minus 3 squared. I'm going to FOIL it out. Okay. And then collect like terms. Let's see. There's t squared, and 4t squared. So that's 6t squared. And then there's 6t minus 12t. So that's negative 6t. And then there's a constant 9 and a 9. Okay. All right, this is a quadratic function. Actually, I don't have to use calculus, right? This is a parabola. So I know how to find the vertex. Maybe I could just use pre-calculus to solve this. Let's do that. All right. So parabola has a vertex when t equals to negative b over 2a. So this is when you have a quadratic that looks like this, at squared plus bt plus c. So in our case, our a is 6 and our b is negative 6. So let's see, if I plug in negative 6 into b, I'll get positive 6 divided by 2 times 6, which is 12. Okay. So that means, so what does this mean? This means when I plug in t equals to 1/2, that's when the line is closest to the point P. So let's plug it in. I'm running out of room here. Okay. So let's see, I have 6 times 1/4. So 3/2. Minus 6 times 1/2. So that's just negative 3 plus 18. Okay. So that's 3/2 plus 15. Or that's 16.5. Okay. All right. That's not quite the answer. We squared it. We squared the distance to make the problem a little bit easier to compute. So the true distance is the square root of that, right? So compute the distance. So the final answer, which I'm going to write in the corner, is the distance is equal to square root of 16.5. Okay. Moving on, next one. All right. Okay. Compute the angle and the intersecting point between the line x equals to y over 2 equals to z minus 1 over 3. So this is in the symmetric form of a line and the plane. Okay. So we have a plane and we have a line. Okay. So we want to find where they intersect. So that's one goal. And we also want to compute the angle it makes with the plane. Okay. All right. So let's find the intersecting point first, and then we'll tackle the angle question. All right. So I think I want to, for this problem, I want to work with the parametric form of the line. So from looking at that equation, I know that the directional vector is the denominators, right? So 1, 2, 3. Okay. And we know it passes through the point, I'm going to call this point P, 0, 0, 1, right? 0, 0, 1. Okay, so if I want to write the parametric form of the equation, I can take the point coordinates and add t times the directional vector. So t, 2t, and 1 plus 3t. Okay, so all I've done is to write the symmetric form into the parametric form. And to see where they intersect, I take this equation and plug it into the equation of the plane. Okay, so x is replaced with t, and y is replaced with 2t, and z is replaced with 1 plus 3t. And all that should add up to 0. All right. Let's see. So let's collect the t terms. So t minus 2t plus 3t adds up to 2t. So they intersect when t is equal to -1/2. I could actually plug the t value into the parametric form to get the actual x, y, z coordinates of where they intersect. So let's plug it in. So x becomes -1/2. Y becomes 2 times -1/2, so just -1. And z is 1 plus 3 times -1/2, so -3/2. So that's -1/2. Okay. Okay. So the point on the intersection is going to be -1/2, -1, and -1/2. Okay. All right. And I can kind of double check that if I plug those x, y, z in there, it does satisfy the equation of the plane. So it is on the plane. All right. Now let's look at the angle. So this is a little bit more difficult question. So the line makes lots of different angles with the plane, depending on where you place the protractor. But again, when people ask for intersecting angle, they usually mean what is the smallest angle they make with the plane. Note that this is the largest angle it makes with the plane. Okay. So let's look at which direction this line is oriented and also the plane, right? So we have the directional vector for the line that's given by the vector 1, 2, 3. We also have a normal vector for the plane that's perpendicular to the plane itself. If, let's see, if we find the angle between these two vectors, that's not quite what we want, right? What we want is, I hope this picture makes sense. So this is the plane. This is a normal vector. And this is the directional vector. If we find this angle, what the angle, what we really want is 90 degrees minus that angle, or pi over 2 radians minus that angle. So that should be my final answer. And I know how to find angle between two vectors. So let's see, the normal vector for the plane is the coefficients of x, y, and z. So 1, -1, 1. And I know the directional vector for the line is 1, 2, 3. Okay. I need to compute the dot product between them. Let's see, 1 times 1, 2 times -1, and 3 times 1. So 4 minus 2 is equal to 2. I also need to compute the magnitude. Okay, so that's the square root of 3. The magnitude of the directional vector is square root of 14. And the angle is going to be arc cosine of the dot product, which is 2 divided by square root of 3 times square root of 14. And that's not my final answer. My final answer is pi over 2 minus that. Okay. Now, this is not going to be a nice number. So I'm just going to leave it in exact form and call it good. All right. So that's that problem. Okay. All right. So I think this is the hardest problem we have so far. Compute the distance between two skewed lines. So we actually looked at these two equations lines last week, and we computed that they're not parallel and they don't intersect each other. So what that means is that one line kind of goes above the other one. Okay. All right. So how do we compute the distance between them? One way to do that is to find kind of, I guess you have to find the closest point on one line to the other line, and then the closest point from the other line as well. So what you could do is this. You can kind of use the idea from the first problem that we did. So we could take any 2 points so 1 point from the first line and another point on the second line, and look at a vector between them. And as long as we have this normal direction, the vector that's perpendicular to the both directional vectors, we can kind of project onto that and get the distance between them. I don't know if this visually makes sense to you. So imagine kind of you're looking at straight at, so I'm looking at this picture that's supposed to be my eyeball, directly from that line. So the point P is on this line, and point Q is somewhere on this other line. if you can find this direction that's perpendicular to both lines, then we could just kind of project onto that and get the distance between the two lines. Okay, so if you accept that, this will actually give you the distance. Let's compute it. Okay, so let's find 2 points on the line. So for this, we're given parametric equation, so we can just kind of plug in maybe t equals to 0 and s equals to 0 and find 2 points. So I'm going to call it point P. What we get when we plug in t equals to 0 into the first line, 1, -2, 4. And I'm going to call point Q second line when I plug in s equals to 0. Okay. And I drew this line PQ. So I'm going to take the coordinates of Q and subtract coordinates of P from it. So 0 minus 1, 3 minus -2. And let's see, -3 minus 4 is -7. Okay. All right. Now I need to find the perpendicular direction to both of the lines. And I can get that direction by taking the cross product between the two directional vectors for the lines. So let's see. I don't know if I have enough room. So the directional vector for line 1 is the coefficients of the t. Okay. The directional vector for the second line is the coefficient for the variable s. Okay. Let's compute the cross product. Okay, to get the ith component, I do 3 times 4 minus 1 times -1. So 12 plus 1. To get the j component, I do 1 times 4 minus 2 times -1. So 4 plus 2, so that's 6. And then I had to have a negative sign in front. And then to get the kth component, I do 1 times 1 minus 2 times 3. So 1 minus 6 is -5. And I'm going to mentally check to make sure this vector is perpendicular to both 1, 3, -1 and 2, 1, 4. So 13 minus 18 plus 5 is equal to 0. And 2 times 13 is 26 minus 6 is 20. Minus 4 times 5 is going to be 0. So this works out. So 13, -6, -5. Okay. So all we have to do is now take the vector PQ and project it in this direction. So component of PQ in the direction of this D1 cross D2. Okay. So I take the dot product. With this cross product, 13, -6, -5. and I divide by the magnitude for each of these. I usually compute these separately and then put it together at the end. I wish I had done that. Okay. Let's see. Okay, so the numerator is going to be negative 13 minus 30 plus 35. There's no way I don't need a calculator for this. But yeah, okay, so 1 plus, okay, so square root of 75 and square root of 230. So let's see, negative 8 over square root of 26250. Okay, so okay, the distance can't be negative, but I just take the absolute value of this, right? It's because the normal vector that we got was pointing in the opposite direction from the actual line. But that's how we compute that one. Okay. All right. I think this was going to be a long video, so let's stop it here. Feel free to ask questions about any of these problems on the Discord or through email. These problems are hard, and you know, these 4 questions aren't exhaustive, right? There's other geometric questions that I could ask you, right? So you might, in preparation for the next quiz, maybe you could ask questions like, what are the possible distance between these objects? What are the possible angles we can make with these objects, maybe between 2 planes? What are the intersections between these objects? So all of those combination could be asked, right? So I hope you get to practice that also in the homework as well. Okay, let's end it now. I'll see you later.